So thanks for the nice introduction. So let's continue with the discussion. And let me first recap what I have talked about in the last lecture, right? So the idea of this fuzzy sphere regularization is nothing mysterious, right? It's very similar to what people were doing in the past, where you consider some quantum mechanical model realizations of phase transitions that could realize, for example, 2 plus 1 DCFTs. And to quantum Hall people, right, then the particles on lambda levels is a very natural place to play with this game, right? And here, quantum Hall is really great for this purpose because you can easily put quantum Hall or lambda level on sphere, and then for CFT, the CFT on sphere really enjoys a lot of very nice properties that is absent in any other geometry, right? That's why quantum Hall is really the key for this regularization. And on sphere, the CFT on sphere has many nice properties. One of the most nice thing is that you have this so-called state operator correspondence, meaning that for the eigenstate of the quantum Hamiltonian, it will be in one-to-one correspondence with the scaling operators in CFT, and particularly the energy gap will be the scaling dimensions of the CFT, right? And then to get scaling dimensions, we can just diagonalize the Hamiltonian to analyze the low energy spectrons, and then you get all those numbers that would take others like millions of CPU hours to get. So and here we have the results for 3D icing, right? It works miraculously great, and this really led to a new era for us to study CFTs, 3D CFTs, right? We can do it very fast with very small number of spins, and we can access almost everything, right? In the past, even if you spend like millions of CPU hours, you can only get very limited informations. Okay, and so now in this talk, so in the last lecture, right, we were using 3D ICCFT as a benchmark to say how good this method is. And of course, it will be more exciting that we can use this method to study open problems that were not that people were not able to do in the past using other methods, right? And this is today's lecture about. And in particular, I will talk about the Chen-Simons meta theories. So those theories describe the phase transitions between quantum Hall states, right? Like different phase transitions between quantum Hall at different plateaus and so on. And then I will talk about how to generalize this scheme to study fermionic CFTs. And then a nice example is the so-called super icing CFT. And if time allows, I will talk about like conformal defect and the boundaries. And I will end this lecture with some interesting conclusions and outlook. Okay, so I don't think I need to say much about fractional quantum Hall state, right? And we know that there are like many plateaus. Many of those are called so-called Gen sequence. And a very interesting question is to consider phase transitions between those plateaus, right? That's what Ilya has talked about. And in this, for phase transitions in quantum Hall, in fact, what the disorder plays a crucial role, right? And that's not the type of phase transitions I'm going to focus on. Instead, I will play with the phase transitions without disorder in the Klein limit, right? Such phase transitions won't be possible in the quantum Hall context, but thanks to the recent development of fractional quantum Hall on lattice, so now, so here we don't really need disorder to stabilize those quantum Hall state, and so for phase transitions, we can also study the disorder-free version. So there are two types of such quantum Hall effect would be interested. One is that you still need a magnetic field, right? It's like lattice plus magnetic field. And for this type of quantum Hall, fractional quantum Hall effect, the right way to think about it is that you start with lambda levels, and then you get weak lattice potential comes from Murray pattern, and those lambda levels could split into sub-bands, and then you can partially fill those sub-bands. You can get different filling factors like fractional quantum Hall or fractional Chen insulator. I think in this paper they call this as fractional Chen insulator, but you may have a different opinion because it has magnetic field, right? And as we know, the more recent exciting development is that you can even get those fractional quantum Hall state without magnetic field at all, right? Experimentally, and to me, of course, those experiments really you open a lot of very exciting properties, and to me, what really makes me excited the most is that it offers new opportunities to study phase transitions, which presumably are CFTs in experiments, right? Those are phase transitions that does not require disorder, right? Okay, so and one thing we did in the past was actually just the old version of this fractional insulator or magnetic field plus lattice potentials. They observe a lot of plateaus. I think each line corresponds to one fractional quantum Hall state. And you can see that there are intersections between different lines. And those at each intersections, you can actually realize certain type of phase transitions. And this leads to a new family of quantum critical points, which can be described by this so-called QED3 Chen-Simons series. So the theory will have several flavor of Dirac fermions coupled with a U1 gauge field, and the U1 gauge field will could have some Chen-Simons levels. So those theories actually, you can call their transitions between different gen states, right? And yes.
That's one.
Yeah, they're just a composite fermion Chen numbers. Yeah. And a nice thing is that here, due to lattice potentials, you can use translation symmetry to make multiple flavors of Dirac fermions to be gapless simultaneously. So you don't need any extra fine tuning to realize this entire family of this Chen-Simons matter theories. Okay, so and today, yeah.
For them, what time the tracking coming to view in my
basically there's no effort because it's very hard to study. Yeah, that's why this fuzzy sphere is really exciting, right? Because finally we can study this. So and here I will focus on probably the simplest example of theory that among this entire family. And this theory, you can call it like confinement transition of chiral spin liquid or confinement transition of 1/2 bosonic Laughlin state. So the transition, as its name suggested, right? The transition is between this 1/2 bosonic Laughlin state and a trivial phase. By trivial, I mean it's a gap phase. There's no symmetry breaking. There's no topological order, right? Complete trivial. And then you can ask, can I have a continuous phase transition between them, right? So I think almost 3 decades ago, people already wrote down theories, Lagrangians, that potentially can describe these phase transitions. The idea is that you consider gapless boson, a fermion coupled to a Chen-Simons gauge field. And as Liang was just suggesting that, indeed, the one physical way to think about that is that is some phase transitions of composite boson or composite fermion, right? So one theory is that the theory is like one boson coupled with U1 level 2, right? It's Lagrangian is like this. So this boson is nothing but composite boson, right? So then you can think that depending on composite boson condensing or gapped, right? You will get either this one-half Laplace state or the trivial phase, right? And then when the boson is critical, you get the critical phase transition, right? And the other theory that you can roll down is that you use composite fermion, and then this phase transition is really just like the Chen number changing transition of composite, right? And I think, these two papers wrote down these two theories separately, and indeed recent study suggests that those theories would be due to each other, right? But this is Lagrangian, right? We know that for Lagrangians involving a gauge field, right? The gauge field will be strongly interacting. It might be the case that the gauge field will really make the phase transitions first order instead of continuous, right? So it was not known for many decades that whether this simple Lagrangian could really give you a continuous phase transition or not. There were even no effort trying to study that because there's no method you can use to study that. Yeah, you cannot use Monte Carlo because it has psi problem. Okay. Yeah, because it has one flavor dual fermion. Yeah. It's like you start with even flavor of fermions and then you gap out auto. Yeah. All right. So and even more spice to this story is this duality conjecture, right? As I said, originally this boson theory and the fermionic theories that is very natural to expect. They are due to each other, right? And later, high-energy people proposed this so-called level rank duality, was suggesting that indeed there are another two theories which may potentially also due to these two theories. So those new theories will involve non-abelian gauge field instead of abelian gauge field, right? It's like one boson coupled with SU2 level 1 or one fermion coupled with SU2 level -1/2, right? So, and this level rank duality is something you are probably familiar with, right? If you just look at Chen-Simon theories that, SU2 level 1 is actually a abelian phase, right? It's secretly just 1/2 Laplace state, right? So the level rank duality was just using this fact and proposed the dualities for those strongly interacting potentially conformal fixed point, right? And one interesting prediction is that if you look at the two non-abelian gauge theories, you will find that the theory has actually SO3 global symmetry, right? But those two U1 gauge theories only have a U1 global symmetries. This U1 you can think is just the charge conservations. So then the prediction is that indeed for this confinement transition of 1/2 bosonic Laplace state, there will actually be an emergent SO3 symmetry, even you don't have it microscopically. So, yeah, and another more newer development is that people propose that for these phase transitions, if you just dope it with fermions, it will actually lead to superconductors. So it's called, they call this anion superconductivity from topological quantum criticality. So I feel it's a very interesting proposal, so let me spend some time to explain it. So the context for this proposal is for this Hofstadter-Haber model on triangular lattice. So so you can say that so you consider spin 4 fermions, or let's say electrons, right, hopping on the triangle lattice, and it hops with a phase, right, and you can choose the phase, let's say for each triangle that's pi/2 flux, and then you just add the on-side Haber interaction, right? It's a very simple Hamiltonian, and you can easily understand that, let's say, if you don't have a Haber interaction, right, I just have tight binding model and I solve the band structure, you will find that you will form Chen band, right? And if the filling factor is 2, then you will get Chen C equal 2 Chen insulators, right? This Chen number 2 just comes from that you have spin up and spin down, each form Chen number 1 band, right? And what's a little bit more non-trivial is that if you crank up the Hubbard interaction, right, make it very large, and naturally because the filling factor is 1, so then I will get Morton insulator, right? And but it turns out that is not a trivial Morton insulator. It's the spin degree freedom of this Morton insulator is non-trivial. That it forms this so-called chiral spin liquid, and this chiral spin liquid is, in terms of topology order, this chiral spin liquid is really just 1/2 bosonic laughing state with this semiotic statistics. So, and for this transition, the thermal Hall conductance actually changed from 2 to 1. Okay. And what's interesting is that at this critical point, at this phase transition point, if it is a continuous transition, the single electron gap is actually always finite. Yeah, it's a bosonic transition. So in the entire phase diagram, the first single electron is always gapped, including the phase transitions. But what's interesting is that the Cooper pair gap will be vanishing, right? It's guaranteed by the universality as long as it's a continuous transition. So now, as a simple-minded person like myself, I would naively just expect that now if you dope fermions, right, because single electron gap is finite, but the Cooper pair gap is 0, right? Then fermions, of course, will form Cooper pairs, and then they will form superconductor, right? They did some numerics to show that indeed there's a superconductors, right? If eventually it really turns out that you can get superconductors from this way, I really feel it's a very cool idea because it's a superconductor from universality, right? It's really universal physics lead to superconductors. Not you don't need to worry about microscopic energetics and so on. The superconductors is guaranteed to be there by the beauty of the CFT, let's say. Yeah.
Is that what you say about what do you do at the good capta?
I think so. But I might be wrong. I think it's D wave. Yeah.
I think there.
It's
current state about activity.
Yeah. It's weak pairing. I think it has 2 Major chiral edge mode. Yeah. That's what I thought. But yeah, I might be wrong. Yeah. But the key question for this beautiful story is that whether this phase transition is really continuous phase transition, right? And this is a problem that we can tackle using this fuzzy sphere approach. So, and what we need to do is that we consider this boson fermion mixture system, and indeed this type of model has been studied by one of the organizers, Kun Yang, in the context of cold atoms. So as you will say, it's actually been very natural to consider such problem in the cold atom systems. So the model is like this. So I have 2 flavors of fermions and 1 flavor of boson, and they carry different electric charge. So the fermions will carry electric charge 1, and the boson will carry electric charge 2, right? So that means you can indeed convert 2 fermions to 1 boson, right? Using this V dagger F1, F2 term, right? And in cold atom, that's really like Feshbach resonance, right? You can use it to make fermions bound to 1 boson, right? Okay. And and here, these 2 flavors of fermions, naturally you can get an SO3 or SU2 symmetry out of it, right? So this is the Hamiltonian. The first term is the total density square, which also appears in this ISIM CFTs we discussed in the last lecture. So physically, you can think it as some term that help you to suppress the charge fluctuations. But I still feel there's some mystery that we don't understand, that why this term always helps us, right? The second term is this boson fermion conversion term, right? You P dagger F1, F2, right? You can convert them. And the last term is the chemical potential, right? Which will control where the particles are, right? So you can, whether there will be fermions or there will be bosons, right? So now you can consider two extreme cases. That is, if the chemical potential is very negative, right? And then all particles would like to be fermions, right? And then and we choose the filling factor that if all the particles are fermions, then I will just get the lowest down level complete field, right? That's like mu equal to integer quantum Hall effect, fermionic integer quantum Hall effect. And now if the chemical potential is very positive, right? And then all the particles would like to be bosons, and then you can easily convince yourself that if that happens, the filling factor for bosons is 1/2, right? Then naturally I will get 1/2 bosonic laughing state. So now you could expect that by tuning the chemical potential, I can realize these the phase transitions between these two, right? That's the model. Okay, so now the first thing that we can check is that whether at the phase transition, the gap, whether it's closed, right? For CFT, we should expect that the gap will behave as 1/r, or one that is like proportional to the NF to the power -1/2, right? So here is a plot like with different system size, and you can see that we rescale the energy gap with this radius r, and then you can see that indeed they coincide at one point, right? And that tells us that the phase transition is probably happening around this gap closing point, and on both sides it's consistent with a gapped state. We can also do this. We can also directly check the energy gap, right? There are actually different types of excitations. Like there is this singulated excitations. You can say it scales to 0, and there are like magneto-roton excitations, which is present in most quantum Hall systems, right? And we find that actually they are gapped. And there's also a charge gap, and it also stays gapped, right? So those are the very simple computations, but we should not view them as the conclusive evidence for the continuous phase transitions. On the sphere, there's something much cooler we can do, right? This like the state operator correspondence. So then we can analyze the energy spectrum to say whether I get those conformal towers, right? So this is the results for conformal towers of the singlet and the conserved current, right? You can say, again, you say this beautiful conformal towers, and which is a very strong evidence confirming that it's a continuous transition with conformal symmetry. And one thing I should mention is that in this model, there's essentially just one tuning parameter, right? This chemical potential, and by just tuning this single parameter, we can achieve very good quality of the conformal symmetries. And among all the operators, we can of this CFT, there are only two relevant operators. One is a singlet operator, which is the tuning parameter for the phase transitions, and we get its scaling dimensions. And the other operator is this conserved current, which exists for any CFT with a continuous symmetry.
Anything from something better, but right about thing the shit takes it.
Yeah.
What shit you scared? Wait, you fuck on.
No, shift is fixed for the state.
The shit is different.
Yeah.
So do you have to make a
Yeah, we have, but the choice is that the particle number will tell us, right?
the period?
Yeah.
The shift is actually top very good.
No, it's not off. The flux are different.
Yeah.
Yeah.
You do the calculation.
Yeah. It's
But
right. Yeah. So it's like the flux of the bosons is like 1/2 of the fermions, or it's the other way around. But then the number of orbitals is like 2s plus 1. So this actually take account of the shift, automatically match the shift. Yeah.
or the conversion.
So let's say the flux of fermions is s, right? Then the flux of boson is 2s, right? And then the number of orbitals of fermions is 2s plus 1, right? And maybe I should write. It's actually very fun fact. So let's say the fermion has flux s, boson has flux 2s, right? And then the number of orbitals is 2s plus 1. So that means number of particles is 4s plus 2, right? And then the bosons, the number of orbitals is 4s plus 1. And when you convert all the particles to bosons, the number of particles is 2s plus 1, because 2 fermions go to
The shift act match.
Yeah, shift matches magically. Indeed, for even more complicated phase transitions that we consider, it always matches. Yeah. I think there's something deep inside it. Actually, I can come back to this point later in another model, which makes this even clearer what is. Yeah.
The DFT, the FTP, and what the line.
It has 4 dual descriptions. One is that just a single boson coupled with SU2 level 1. Yeah. So, and this is a spectrum, and we also have more evidence, right? Like the conformal correlators, which I also showed for icing, and we also find that the scaling dimensions is pretty robust as we change, let's say, add more interactions and so on to say how it depends on those interactions. And most importantly, we can construct those so-called conformal generators and then apply those conformal generators to check the conformal algebras. Yeah, all those things are consistent with CFT. Okay, so this is one example, and now let me move to another example that is the fermionic CFT and super icing. Okay, so the fermionic CFT just means that it's CFT with a local fermionic operators, right? All the examples I have talked about are bosonic CFTs, like icing, right? Like this confinement transition of Laughlin state, right? You don't have a local fermion operators, right? And the examples of the fermionic CFTs are like just free Majorana fermion or free Dirac fermions. You can also make it interacting by couple the fermions with bosonic Yukawa field, right? This is sometimes called Gros-Neveu Yukawa CFT, right? If you have just a single free Majorana fermion coupled with Yukawa field, then this theory actually has emergent supersymmetry, right? I think it's the simplest example of the super symmetric CFTs. And I would say that those fermionic CFTs are more relevant for materials, like let's say Moray materials or any materials built of electrons, right? If you have phase transitions, it's very natural to expect you have a fermionic CFT, right? Because you do have fermions in a system, right? And once those fermions are gapless, right, it will give you much cleaner experimental signatures, right? Because we know electric signals are much easier to measure compared to the magnetic signals. right?
It's about the more or back to jump by
Yeah. Yeah. But this fermionic CFTs are somewhat challenging for fuzzy sphere approach. The reason comes from the so-called magnetic spatial symmetries, right? So remember that although our model, right, are mostly built using fermions, right? But those fermions, just like Ising transitions, but those fermions cannot really be the part of CFT. It has to be decoupled in the infrared. The reason comes from this magnetic spatial symmetries. For example, if you just consider, I have this system on a flat space, right? And then we know this famous magnetic translation symmetries, which is the projective for the spatial symmetries. But such symmetry does not exist in any CFT, right? So then to have a CFT emerge, you have to that those microscopic fermions to be gapped, right? They were decoupled in the infrared, right? So then in the CFT, all the operators in this approach, all the operators will be charge neutral such that it won't see this magnetic spatial symmetries, just like the Ising examples. The Ising spin operators will be like this density operator, which is a fermion bilinear, right? So now, then you naturally expect that if I study CFTs in this context, I will always get bosonic CFT operators, right? Just think about any, let's say, QFT we learn in textbook, right? You don't have this magnetic translation symmetry. It's just ordinary translation symmetries, right? Yeah. Fermion charge. Any charged particles have to decouple. Yeah.
You'll be calm.
No.
It is the best way. This the orange one day have part to and up the piece that.
Yeah. It has to have some, let's say, Hall conductance and so on. Yeah, those cases. Yeah. So now that this comes a very funny irony, that is to have fermionic CFTs, we have to include boson in the game, right? So we need to consider boson fermion mixture such that I may be able to realize fermionic CFTs. So and turns out that this idea worked. So again, we are consider a boson fermion mixture, but this time the boson and fermion will carry the same charge. So then I still can convert them if I by converting pairs of fermions to pairs of bosons, right? This is captured by this term. So then in this system, then you can know that I can build. Yeah.
With the liberty, but one back that
Yeah. That
the program is can got the step.
Why? Because they carry same charge this time.
Right? God.
Yeah.
It's not imagining for them to come up here. You put up.
No. So that's saying it's a theoretical model. I don't know if there is any experimental system can realize this model. Yeah.
That's a fermion find both.
It can tell pair of fermion to pair of boson.
I bought a thing faster. We can't.
No, it's they carry same charge, right? So it's you turn a charge 2 object to a charge 2 object, right?
You're saying that that's okay. This program is okay. The way you typically two fermion will carry.
Yeah.
You're saying that the both the fermion together also carry charge 1.
No. The 2 fermions carry charge 2. 2 boson also carry charge 2, right? So then
Get to go.
yeah. Yeah. So now, then you can build local fermion term. By local fermion, I just mean operators that is charge neutral, right? Now this F dagger B and so or B dagger F, right? This is an operator that doesn't carry any charge, which could, in principle, be part of the set T. Okay, and then again, that's the Hamiltonian. It's very similar to the one we had before, right? We have this total density square, which suppresses the charge fluctuation. We have this boson-fermion conversion term, but this time it's B dagger, FF. This D is just the differential operators on the sphere. And last term is a chemical potential, again, controls how much the particles are in the fermions or in the boson sectors. Okay, so, and we consider a case that the filling factor is 1. So then that means if all the particles are fermions, then I would just form nu equal to 1 fermionic integer quantum Hall effect state. If all the particles are bosons, then the filling factor is again 1, and I can form this bosonic Fabian. Now, this shift that Kun asked actually appears here in a more dramatic way. So the shift of bosonic Fabian and fermionic integer actually differ by 1. So now in this game, I'm always, so the number of particles of fermions and bosons in two extreme limits should be the same. That means the orbitals of the boson should be one, it's less than the fermion by an integer 1, right? So that means their flux actually differ by 1/2, right? So remember that, so that means this composite, right, F dagger B, should always carry half integer, right? Just because F and B, they have their angular momentum differ by 1/2, right? So, but that is exactly what we want, right? Because we know it's a fermionic, it's a fermionic operators, and eventually, if there's a Lorentz invariance, this spin statistics theorem tells us that it had to carry half integer. Now, this is nicely captured, automatically taken care by the shift of the quantum Hall effect, right? So, and okay, and this is a model. We understand the two extreme case, and then we can, and then it's not entirely clear whether there will be a direct phase transition between this fermionic integer quantum Hall and bosonic Fabian, and we studied it numerically, and we find is actually there's an intermediate phase. This you can call it topological superconductor. I don't know whether that's a right terminology, good terminology, but the nature of this phase is that it on the edge it has 3 Majorana fermions, right? But it doesn't have topological order, right? You can think it is a topological superconductor, but the model we have already explicitly break the U1 conservation of the fermions by hand, right? But then that's the phase diagram, right? So we have this fermionic integer quantum Hall, right? You can think that its edge has a complex chiral complex fermion, or in other words, 2 Majorana fermion, and the intermediate phase has 3 chiral Majorana fermions. So that's why the transition between them is actually just a single Majorana fermion.
Yeah. Then in the previous work, but then what they asked was about the position for what happened when both the fermion, but for the boson.
Yeah.
And here, what is the y-axis?
T is the hopping. Yeah. This conversion. Sorry.
The T, okay, see this.
Yeah, a step. Yeah.
Yeah, in this bit diagram, you show that there need to be a immediate.
Yeah.
But I want to trust you.
Yeah.
Yes, that is something much.
Yeah.
That my equation.
Yeah.
I don't think trying to possible.
I mean, it's really just a terminology.
Operating.
Yeah. It's really just a terminology because we already break the U1 symmetry explicitly by hand. Yeah, total U1 is always preserved. Yeah, I mean, by topological superconductor, I really just mean that if you look at this, if you think that's say, just look at the fermions, right? Its particle is not conserved, right? It's already broken by hand. Yeah, right. It's I don't know what's a good name for that. To Heinrich's theory friend, I would just call it SU3 level 1, but I think most people will feel off if we call it in that way. Yeah, but you can,
Oh, right. Excellent.
No, the thing is that there's no longer, there's no spontaneous symmetry breaking. It's really just, you can say, it
is a fully gap.
It's a fully gapped phase. Yeah, or in other words, I can say this in Kidav's this 16-fold way, it's nu equal to 3 state. Yeah, that's it. That.
Fully gap.
It's fully gapped state, and on its edge, it has 3 Majorana fermions. I would love to know what's the best name for it. Yeah, I know it's very confusing to call it, but in literature, people also sometimes call it in this way. Yeah.
Some kind of composite.
Yeah. You can call it quantum hall of Majorana fermions. Nu equal to 3 quantum hall of Majorana fermion.
Much better, man.
Okay. Yeah. So, and then in that terminology, this fermionic integer quantum hall is like nu equals 2 integer quantum hall Majorana fermions, right? So then the transition between them will have single Majorana cones, right? And the transition between this Majorana quantum hall state to bosonic Fabian is actually described by Ising transitions coupled with the Z2 gauge field, right? You know this bosonic Fabian, you can think of it as a pairing of composite fermions. No, it's straight half. It's bosonic Fabian. Yeah. So in the second transition, there's no thermal hall change, but the topological order changes. Yeah. Yeah, it's as I said, right, as we discussed, it's not a good name, right? There's no spontaneous symmetry breaking. Yeah. So, okay, now let's focus on this Majorana fermion CFT. We also studied this Ising star, but it's not as interesting as its fermionic CFT. So again, this is our Hamiltonian. We have 2 tuning parameters, and we find that the results, for example, the spectrum, is not very sensitive to this conversion strengths, right? For this T taking value in this wide window, it seems the result spectrum is more or less the same, right? Which you can also say from this phase diagram, you see this part in my phase diagram, right? The line is almost vertical, right? And one interesting thing is that for the T lies in this window, the CFT happens almost exactly at mu equal to 0, right? And this is the spectrum, I think, for T equals to 0.3 or 0.4, I don't quite remember. But then you see the spectrum, right? The low-lying operators actually aligns well with the theoretical expectations. I can say that for large scaling dimensions, there are some off, but you can say the trend is going to the right direction, right? And as I said, right, what really makes it interesting is that to realize these phase transitions, it seems that I don't need any fine tuning, right? Which, if you think of the model more carefully, there's no parity symmetry in the model, so this doesn't come from a symmetry reason. So we still don't understand why it happens exactly at mu equal to 0. But one fun fact is that when mu equal to 0, the Hamiltonian actually take a very simple form, right? As I said, the B dagger F is just the fermions. Then you can write down the 2-component fermionic spinor, like 1/2 minus 1/2. One is B dagger F, the other is F dagger B. And then this conversion term is nothing but the kinetic term that we have in free Majorana fermion theories. Okay.
Good question.
I mean, this.
But
Yeah, that it has two levels, and we just have it. Yeah.
You go back with here is the then it's just the database is all the types, right? Just the base has and can
Sorry,
we call it the second entity by forms.
you mean the chemical potential?
On the second.
This one? That's what we have, right? So
But the database there at that point.
the content, right, is this condition conjugate.
Not yeah, the second.
Yeah, gradient has, because it's fermions, right? If there's no gradient, it vanishes. But we don't have any flavor symmetry here. So yeah. So then, this is really the minimal Hamiltonian you can write down, and then you have to put a gradient there, and it turns out that gradient is nothing but this, what we have for the free Majorana fermion Hamiltonian, right? It's
I mean, yeah, at this point, shouldn't I? You're out. You're up there for me.
Yeah.
And you're taking the test to pencil with the what the fermion, they are fermion dying there. They're dying.
yeah.
I think that's what was on the step.
Yeah.
Coming about the worst time in the world. The first cut that's based about fall.
Yeah.
But
Yeah, exactly. Yeah, exactly. Yeah. That's actually the picture to think about all those safety. Most of the safety is in this context. Yeah, it's charge neutral. Yeah, you always have to make it charge neutral. Yeah. So this is a spectrum, and then the funny and also mysterious part is that why phase transition happens at mu equal to 0, it cannot come from any symmetry reason, and when this mu equal to 0, the Hamiltonian is really just like a quantum field theories to start with.
The time that talented going to remote to 10 years there's a both gap, both gap. We can tell banks will go usually deep. I don't for content. It can be I didn't work in 10 bar.
Let's talk about maybe yes.
The station that put these did not fall. I don't call it modern there.
Yeah.
Okay.
Yeah. My naive guess is that maybe at mu equal 0, this model is secretly integrable. Yeah, so I don't, but it would be something that really worth to understand. Okay, now let's go to the super icing, right? We have single Majorana fermion, and then if you, as I said, if you couple with a critical scatter, people find that it will have emergent supersymmetry. I think it was first pointed out by this paper by Grover, Shen, and Wishwanath, and they propose that, and it's very easy to, at least theoretically, think that on the surface of 3 plus 1D topological superconductors, right, you can have single Majorana fermions, and you may realize this super symmetric set T's, right? So then we want to also realize this on fuzzy sphere, right? So if we look at back to the critical scatter, that is icing or free fermion, Majorana fermion model, you can actually notice those models are very similar. So you can, for example, for critical scatter, what you can think is that I have two species of particles, right? One species that's called F0, the other is called F1. Both of them are fermions, right? If you put all the particles in the F0, that's indeed correspond to a polarized state, right, of the transverse icing model. Now you can start to excite one particles, and then this one particle excitation indeed correspond to a sigma field or phi field that you have in the quantum field theory. That's actually pretty much like what Liang was suggesting. And then go to the fermions. That's exactly what Liang was saying. That now we just replace this second species of fermions with bosons, right? And then the rest of the picture is the same, right? I excite one particles from fermion to boson, then that's correspond to a fermionic mode that becomes part of the set T, right? So now naturally you would expect that now we just combine these two things together. I still have the same vacuum, this F0, but now I have one species of fermions, one species of bosons, right? If I excite particles from F0 to F1, I get this critical rail scatter. If I excite particles from F0 to bosons, then I get fermionic fields, right? Then for this model, I may potentially realize this interacting Majorana-Grosvenor-Yukawa theory that has emergent supersymmetry, right? So this is the Hamiltonian we have, right? So you can indeed easily interpret that the first term is what we had for free Majorana fermion, and the second term is what we had for the Ising, right? This Ising interactions, and the third term is like Yukawa, right? You couple the boson and the fermion, right? All of them have the nice QFT interpretation, and then we can have three different chemical potential terms, right? Control where the particles are, right? And in the context of the CFT, I also have three relevant perturbations, because I don't have any symmetries to forbid them, right? So 3-parameter tuning is the minimal thing you need to do, right? So, and then what we did is that we fix all these interactions, right, to some values, to some nice looking values, and then we fine tune those three relevant perturbations and to say whether we can get the supersymmetric CFTs. So this is the specific values we found by just try to make the spectrum as close as the super Ising, right? You see that the size dependence of those three parameters are rather weak, and then we get the spectrums. That's the low-lying states of the super Ising we can get. And here is just one plot for the multiplet, the so-called super multiplet of sigma, right? So it actually contains three conformal multiplet, and those three conformal multiplet, I think that these three relevant perturbations we have, right? So yeah, I won't go to the details, but just showing that it works. And there is indeed emergent SUSI, and this is the results for many states lying with scalar dimension is smaller than 6. And again, we find all the states in this spectrum, at least for this part, they are all CFT states, right? And yeah, maybe I should just quickly, should actually skip this part. So let me maybe just spend 1 or 2 minutes talking about this defect. So we can also expand this program to study the so-called conformal defect or boundary, right? This refers to, in the quantum case, that refers to, for example, you can consider the Kondo impurity coupled with the CFT, or you can consider the boundary, right, of the theory. So all those are inevitable in, let's say, in real experiments, right? And indeed, they also lead to interesting critical phenomenons, right? Which is different from the bulk, which it depends on the bulk, but the details are actually different, like the exponents are different and so on. So we can also apply this to using fuzzy sphere to study it. I don't think I have time to explain it. And one thing I should actually point out is that for the defect, there's so-called a defect G function or defect central charge or defect entropy, which is like the central charge that is monotonic on the RG. It was first pointed out by Affleck and Ludwig. And there's also higher dimensional version and so on. So, and this quantity has never been computed non-perturbatively before us. So we did the first computations. It's a very nice example because later, like 1 year later, people managed to use rigorous conformal bootstrap to compute it, and they get this G functions with rigorous error bar, and you can say that they really they confirm our predictions of these G functions. So that gives us more confidence that this our fuzzy sphere method is really powerful, right? Because most of our things that we have computed is not available for other method. So at the moment, this is really a nice example that confirms our results. So yeah, let me just spend maybe a few more minutes about the try to give you some outlook about this what are the possible exciting things to study in this fuzzy world, right? So of course we can use it as a numerical tool to solve many open problems of CFTs and also QFTs, right? It's like what we are already doing, right? There are really many interesting theories, like those Q gauge theories, right? Like those Chern-Simons matter theories, which describes the phase transitions of quantum Hall, topological order, and so on, right? You can also look at other things like CFTs at finite temperature, which will be relevant to experiments. And you may also heard that the CFT at finite temperature is due to black hole in quantum gravity, right? So all those things, there are a lot of fancy physics now is accessible for us to study, right? Maybe quantum Hall will really teach us to solve all those problems that people care about but are not able to do in many other different fields, right? And to me, even more exciting direction is try to understand why it works so well, right? So it's a strongly interacting gap-least system, right? Why a Hamiltonian with only 4 particles can give us very accurate information, right? So and I don't know the answer, but there may be 2 interesting possibilities that maybe in the end both of them are the reason. So one is that maybe the non-commutative geometry is the right thing to use to regularize QFT, or maybe it's also tied to the 3D CFTs. There's actually a very interesting story behind this by using non-commutative geometry to study QFTs. So it was originally proposed by Heisenberg in 1930s, right? It's way before any technique for this regularization, renormalization was invented. And, the original idea was really use this to cure the infamous UV divergence in quantum field theories, right? So then if you can easily imagine Heisenberg would come up with this idea, right? It's really just like generalizing his uncertainty principle in quantum mechanics in phase space to uncertainty principle, like non-commutativity in the real space, right? He didn't write a paper on this, but he wrote this idea in a letter to his former student Pius. This Pius is this Pius instability. And this idea gets propagated to Pauli, Oppenheimer, and finally it becomes a PhD project of Snyder, and he wrote the very first paper on this using non-commutative geometry to regularize QFT. And many years later, mathematicians have formalized the idea of the non-commutative geometry by Alan Connors, and he also got a Fields Medal for this contribution. So in the past, people have pursued this idea, like using non-commutative geometry to regularize QFT, particularly in string theory community around 2 or 3 decades ago. But one observation is that there's the so-called UV ion mixing. Basically, the upshot is that in the end, if you naively define a quantum field theories in non-commutative geometry, you will not get the usual QFT we want to study, like those 5-4 theories, like those Ising CFTs. You won't get them. You will get some other theories with some non-locality built in, right? So this idea was not successful in the past, but now I think maybe it's a good time to really revisit this idea. How to make this idea work it's probably hidden in quantum Hall physics, right? So at least in practice, we find that using this quantum Hall, right, we can easily study many different CFTs, right? So we need to understand what's the recipe for us in this non-commutative geometry to study to define a QFT, right? And another thing is that it's related to the CFT is that maybe the CFT structure is the 3-dimensional CFT structure is hidden, is related to the lambda levels. And don't think I time to explain this, but let me just show again that, which I also showed in the last lecture, is that one direction really towards that this goal is that maybe we can try to come up with some wave functions that for the CFTs, particularly for the 3D icing, right? I did my try. I wrote down a simple wave functions without any tuning parameter. It has very good overlap with the numerical icing CFT ground state, and the overlap is comparable, right, or even higher than the Laughlin wave functions with the Coulomb potentials. And it also has power law correlation functions, but I don't quite think this is the final correct answer, but it's very interesting, promising directions to pursue. Okay, so now let me summarize. So we propose this new scheme that we call fuzzy sphere regularization to study 3D CFTs. So the basic idea is very familiar, right? We really just study quantum Hall physics and study phase transitions in it. But I think there may be some deep connections with non-commutative geometry, particularly the old idea of regularizing QFT using non-commutative geometry. And the major surprise is really that it just, for very small system size, works miraculously well, which still requires some deep understanding. Okay, so, and practically we can use it to really compute a lot of things. We can apply it to many CFTs, like the conventional symmetry breaking transitions, as well as those involving gauge theories, like Chen-Simon symmetric theories. We may even use it to discover some new CFT that people have never tried to write down. Yeah, let me just stop here and show regulators.